In this video, Florida harvester ants reveal the details of how they dig nests and how they move things around. This story begins with a chance intersection between archaeology and ant nest architecture. Jim Dunbar on the left and Jack Rink were working on an archaeology project that used optically stimulated luminescence to date soil layers. Some of the dates seemed way out of line with the currently accepted story of the peopling of North America. They came to me and Christina Quapich to explore whether ants could deposit soil below ground without exposing it to light, thus scrambling the dates. My research site at Ant Heaven, with its dense population of Florida harvester ants, seemed like the ideal place to carry out an experiment. The project was to plant harvester ant colonies in a column of sand of many layers of different colors. Sand color would then identify the source and deposition location. Jack ordered 2,000 pounds of sand in 10 colors and delivered to Ant Heaven, and we constructed the multicolored layer cake in a 2-meter-deep pit. The walls of the pit were reinforced by plywood to prevent collapse during construction. Here are the sand colors and their thickness from top to bottom. The bottom two layers were 50 centimeters thick rather than 10. Here are the colors in the order from top to bottom. When finished, the harvester ant colony was planted in a screen-bottom cage on the top of the layer cake. The ants dug their nest through a hole in the screen. Ants excavate by forming pellets of sand containing an average of about 160 sand grains. It seems likely that mining pellets and transporting them is done by different workers, as I will tell you later. The color of the excavated sand tells us which layer and what depth the sand came from. The number of grains of each color reveals the rate of digging in each layer. Over time, this is a record of the progress of nest excavation. The daily proportion of each sand color dumped on the surface reveals the relative digging rate at each level. The dates are on the x-axis. First appearance of each layer at the surface tells us the maximum nest depth at that time. Initial excavation is obviously in the top layers, but day by day the nest is deepened and the chambers enlarged, as seen by the relative area of each color in this graph. By totaling the sand of each color over several months, we computed the area of chambers dug in each layer. The upper layers had multiple chambers and some of the deep ones had only one or two. In essence, the void shows the final outcome, at least in principle. The volume excavated from each layer is detectable at the surface. So far, we've used the total amount of each color deposited at the surface to infer the bulk volume and depth at which the ants were digging underground. Many of the pellets that workers deliver to the surface can be collected intact and analyzed individually. Here is an example. And here is another. Note the many colors. When a pellet contains more than one color, it suggests that the miner of the pellet did not take it directly to the surface, but deposited it underground in a different host layer, where it was later reformed into another pellet that included host layer colors before being carried to the surface. The degree of color mixing can be quantified by the Gini coefficient. This index is 0 when there is only one color, and 1 if all the colors are equally represented. Most pellets were dominated by a single color with small amounts of other colors and therefore had small Gini coefficients. Since there are 11 colors, a completely mixed pellet should contain 9% of each color. Pellets with 6 or 7 colors were seen with Gini coefficients of 0.7 to 0.9. So 7 months after planting the colony, we excavated the nest chamber by chamber. Color-mixed pellets suggest that when we dig up the nest, we should find multicolored deposits in the chambers and shafts. As we worked downward, we inspected each chamber and shaft carefully for sand of a different color than the host layer. In the uppermost complex chambers in the native sand just under the surface, there was a great deal of backfilling with many colors, sometimes entire chambers. Note the blue, green, and purple here. Many deeper host layers contained non-host colors. Many colors are visible in the smooth lining of this chamber and shafts. Green and yellow are visible at the intersection of the purple and orange layers. At least 6 colors are visible here. Intact yellow and green pellets are loose in a violet chamber. And abundant pink pellets loose and packed into a chamber in the blue layer. More towards the fashionable orange, yellow, green, and blue here. Overall, counting colored sand grains over 7 months of the experiment showed that about 4% of the excavated sand was deposited below ground. As you can see in this figure, most of this deposition was in the top 30 centimeters of the nest. Below about 70 centimeters, some sand was moved downward, but that isn't shown here. All of this below-ground deposition tends to scramble the OSL dates, but that's a story for the archaeologists to tell. It's not part of our story here. For our story here, we see that transport in ant colonies occurs through sequential caching and transport. This pattern of transport and deposition is most likely carried out by what I call transport workers that shuttle between the nest depth and the top chambers. This organization of work is called series parallel. Workers are largely redundant and need not complete the whole job because others will take it up and complete it. The layer cake experiment played out over 7 months, but a short-term experiment showed that sequential caching and transport actually takes place on a very short time scale. Nicholas Hanley and I dug down next to harvester ant colonies, cut into chambers at about 50 centimeters depth, and injected pink sand. Excavation after several days revealed depots of pink pellets at several levels, mostly in the upper chambers. Pink sand lined the uppermost chamber of this nest. The chamber is outlined in black. Pink sand appeared on the surface within a day or two. Sequential caching and transport of sand is thus a rapid and ongoing process. Seeds are also moved by sequential caching by transfer workers, as the next experiment showed. We prepared 3 batches of seeds, each marked a different fluorescent color. We offered colonies these marked seeds at 3 elapsed times. Foragers readily brought them into the top chambers of the nest. Each colony was excavated after the last batch to determine the location of the seeds. Within an hour, marked seeds were found at all levels of the nest, indicating that they had been cached. Most seeds were in the seed chambers, shown by arrows, within a day. Within an hour and a half, seeds were at many levels, indicating caching, but most were in the seed chambers after a day. Seed collection was poor in this experiment the 2 days prior. This colony quickly moved seeds in stages to the seed chambers in 45 minutes. By day 1 and 2, most of the seeds were in seed chambers, again shown by arrows. Even 15 minutes was enough to move seeds to several depths, although most were still in the uppermost chambers where the foragers had dropped them. This sequential transport system applies to almost all objects moved within an ant colony: sand pellets, seeds, trash, larvae, pupae, and so on. The effect is to divide large tasks into smaller linked pieces and to separate the groups that specialize in carrying them out. The specialization is thus at the group level, not the individual level, where series parallel organization prevails.